Hello and welcome back. I'm Adam with Push the Envelope, the channel that gives you everything artificial intelligence and machine learning. Today we are going to be focusing on part 3 and the final part of the Making a Neural Network from Scratch series. I am super excited to get started. We are going to finally be incorporating everything we learned in the last 2 parts on gradient descent into making a complete neural network. Now, if you haven't seen those previous 2 videos, definitely check those out before you watch this video. You're going to be a little bit behind if you don't, and it's definitely good to understand the fundamentals of gradient descent and the basics of how it works and why it works, because it is fundamental to how neural networks work and how machine learning works. So definitely go check those out right now if you haven't seen them. And for those who have, let's go ahead and get started with this tutorial. Okay, swapping over to our Jupyter Notebook, you can see I have an image up here of what we are about to do. So if you remember from the last 2 videos, we have 2 inputs, and we originally were mapping them straight to a single output. Well, now we are creating a neural network with one hidden layer in between it, and this hidden layer can have as many neurons as we want it to. So we are going to go ahead and do that right now. And as before, I am going to be using NumPy to do all of this. So I'm going to be importing NumPy as NP. Again, I'm going to be using matplotlib, pyplot to visualize my data. And I'm going to use sklearn to make my data sets. Now there's a couple more functions from sklearn I want to import. So from sklearn.model selection, I want to import train test split. That's going to help us split our data into training and testing sets. Now from sklearn.metrics, I want to import accuracy score. And that is going to help us determine how well our classifier is fitting to the data. Okay. As always, first thing we need is data. So I'm going to actually just create a new function called genData. And I'm going to be looking for a parameter called n for however many data points we want. I'm just going to set the default to 1,000. And if you remember in the last video, we used the datasets.makeMoons to make our data. I'm just going to do the same thing here. So make moons, and the first thing it's looking for is the number of data points. And again, I'm going to set the random state to 1 so that everything I do here you should be able to repeat. Now, data is split up into x and y, so I can say my x is equal to the data at 0, and my y is equal to the data at 1. However, the data for the y values is 1 full list, and I need that to be a row per value. So what I'm going to do is I'm going to reshape this using -1, 1. And now it's in the format that our neural network is going to be expecting. So I'm just going to go ahead and show what the data looks like using pyplot scatter. And now I need to transpose the x data in order to get it into the format that pyplot wants. And I'm taking the first element as the first feature. And I'm going to do the same thing, but I'm going to grab the index of 1 for the second feature. So I'm plotting feature 1 by feature 2. And now I'm going to change the color to be the y values. Oops. And I'm going to transpose those, put them in the right order. And I'll just add some other things to it. So I'll do add a title called generated data. I will add some x labels. So x will be our feature 1. And same thing for the y label, except it will be feature 2. And I'll do a plt.show. Okay, we should be good to call this now. And as you can see, we have 1,000 data points, and they are in these arc things that you can see here. The class 0 is the purple one, and class 1 is the yellow one. Now, this looks super simple, and I want to kind of make this a little harder for our neural network to solve. And one way I can do that is to actually pass in something called noise. So I will pass that into the function, and I'm just going to set the default to 0.3. And then within this make moons function, I can also pass that as noise. So noise equals noise. And I'm just going to pass that in here as well. Now, when I set the defaults like this, you don't need to pass them into the function. I just do to make sure that I'm tracking what all the features are and what the values are. But I will go ahead and show you that to show you the difference between the two. And as you can see, with 30% noise, you can still see the crescent shapes, but in the middle, it's a lot more blurry and a lot more overlap. So it should be a little harder for our neural network to pull out the solution. And the last thing I'm going to do is I'm going to use that train test splits function when I return the data. So I'm going to return train test split. I'm going to pass it in X and Y. I am going to, again, fix the random state to 1. And now the other thing I can do is I can say how much data I want to be used for the test set. And that is the parameter test size. And that is going to be a third thing I'm going to pass into my function. I'm going to call it t size. I'm going to default that to 20%. And I'll just pass in 20% as well down here. And I'm going to set test size to t size. And that should be it. Now, when I call this function, I'm going to get 4 things back. I'm going to get x train, x test, y train, and y test. So the x and y values for the training and testing sets. I'm just going to go ahead and print the shapes of each of these. Just so we can see how much data we have and what each of them look like. All right, go ahead and run it, and you can see we have 800 training points and 200 test data points. And with that, we are good to move on to create our neural network. So we're going to be creating the neural network as a class. So I can define a class right now. Sorry, not define. I can do class. I'm just going to call this neural network. And the first thing we obviously want to do is some initialization function. And pass self. Now, I'm actually not going to pass anything with it, and we'll work on what those are in a second. So if you remember the last video, the first thing we did was we initialized the weights. So I'm going to do the same thing here by making weight 1. And that's going to be equal to np.random.randn. And now it's not going to be as easy this time because last time we could have one weight per each input variable. However, if I go back up to the top, we no longer have a input to output mapping. We have to account for all of these different lines right here. And each of these lines have their own weight. So we are going to be creating the first set of weights for the inputs to the hidden layer, so the number of neurons. And then the second set of weights is going to be the number of neurons to the output, which in this case is 1. So we can go ahead and define that right now. And this is the part where I'm going to pass in those different features. So the first one is number of features. So this is the number of input values. The second thing I need to know is the number of neurons in the hidden layer. And the last thing I need to know is the number of output variables. So if I create a new line here and I just create a new variable and I use the class. Now when I define this, I'm going to pass in that I have 2 features. Let's make this 10 neurons. And there's going to be 1 output. So this is what I'm going to be passing into it, and that's going to help us create the weights up here. So within this self, again, the self is going from the input, so the number of features, to the number of neurons, so n neurons. I spelled neurons wrong. Okay, so that takes care of weight 1. Now, again, I'm trying to fix any randomness in here. So np.random.seed, I'm going to set this one equal to 1. I'm just actually going to go ahead and copy this because weight 2 is going to be done in the same way. I'm actually, for weight 2 though, going to change the seed to 2. And we need to change the size of this now. So it's no longer the input features to the neurons, it's actually the neurons to the output size. And that takes care of both of the weights. Now the last thing I'm going to define in here is I'm going to do a default learning rate. And then if you remember, the learning rate is how fast you converge on the answer, how quickly you go down that gradient. And I'm going to set the default to 0.01. All right, and that will take care of initializing our neural network. So just for sanity check, I'm going to go ahead and define it, and it looks good, no errors. Okay. Now, if you remember the gradient descent video, we have 2 functions that we need to make, and that is, the first part is feed forwarding, and the second is backpropagation. So we're going to make a function called feedforward. What is feedforward looking for? Well, it is looking for the x values that we give it. Now, this is where we start to map our input values to their respective weights. So the first one is going to be called layer 1, right? And we are going to take the input, which is x, and we're going to do a dot multiplication. So matrix multiply x dot, and then we're going to do self for the weight ones, right? So taking the inputs times the weight ones. Now, also, if you remember from the last video, not only did we multiply it by the weights, but we had to pass it through an activation function. So we also need to define an activation function. In this case, I'm going to use sigmoid again. And sigmoid is going to be looking for some x value. And I'm going to do it through the return. And I'm going to say return 1.0 over 1.0 plus np.exp to the negative x. So 1 over 1 plus e to the negative x, and that is the sigmoid function. And since we're using NumPy, we can pass in an entire array and it'll give us the value for all of those different values. Coming back down to our feedforward function, we need to pass it through here. So self.sigmoid. There we go. We got from our inputs to our hidden layer. Next step, we need to go from hidden layer to the output layer. So we need to define the output layer. Again, that's going to be using sigmoid as the activation function. It doesn't have to be the same here. So I could use like ReLU or tanh as my activation function here. But then I would have to define those activation functions, and it gets more complex taking the derivatives of the different activation functions. So I'm just going to keep it the same for now, just to make it easier for us in the end. Okay, so this one is looking for the output of the hidden layer. So the layer that we just made, self.layer1. And now we need to do dot multiply that with the weight 2s. So layer 1 times weight 2. And that gives us our output. Right, this will give us y hat. Okay, now that is the first part of the function. Now we need to do the second half of the network, which is doing backpropagation. So I'm going to define backprop. And this is going to be looking for x and y values. So if you remember from the last video, a lot of the functions use the output minus the real results. So I'm going to define D2 as the output, And in this case, like I just said, our output is going to, our y hat is going to be self.output. So self.output minus the y value that we just passed in. So that gives us the helper function for the first, the derivative working backwards. So this is from the output layer to the hidden layer. Now we need to go from the hidden layer to the input. And this is going to be a little more complex. So we are going to take the weight 2's and we are going to dot multiply them with the D2 that we just made, but we need to transpose it. So D2 dot T, and then we need to transpose this entire thing right here in order to be able to multiply it by the derivative of the activation function. So again, sigmoid is our activation function. We need to find the derivative of that. So I'm going to define d underscore sigmoid. And again, this is looking for an x value. So what is the derivative of sigmoid? Well, it's sigmoid times 1 minus sigmoid. And we're about to pass, if I go down here, let me just finish out this equation. So d sigmoid. And what we're going to be passing it is self.layer1, right? So the hidden layer. Now, the hidden layer has already had the sigmoid taken of it, so we don't need to worry about using sigmoid again in this derivative. So instead, we can just return x times 1 minus x. Because, again, this x is already a sigmoid value, so we can just pass this equation instead of reusing the sigmoid function. That makes it a little bit easier. Okay, so we've got our two helper functions here. Now we need to do the weights with respect, the derivatives with respect to the individual weights. So I'm going to call this weight 1 derivative. Now, how do we get that? Well, we are starting with our input, and I need to transpose the input. And then we're going to do the dot product with d1, so this d1 value that we just created here. And that's going to map the inputs with the derivatives, and we're going to get the derivatives with respect to weight 1. Weight 2, sort of similar. We are going to take the layer 1, so self.layer1, so the output of the hidden layer, and we're going to transpose that, and then we're going to dot multiply it with d2. Okay, now that we have the derivatives with respect to the weights, we can go ahead and update the weights. So that would be self.weight1. And if you remember, that's minus equal the learning rate. So self.lr times the derivative that we just calculated. Okay, I'm going to copy this because it's going to be the same exact thing for weight 2. Except for it's going to be the derivative with respect to weight 2. Okay, so now we have updated them and we have put together our neural network. Now I could, if I wanted to, go ahead and outside of this class down here after I define it, I could make a for loop and I could keep calling feedforward and backpropagation continuously in order to train the model. Instead, I'd rather match some of the other packages like Keras or scikit-learn where you can just do a dot fit function. So that's what I'm going to do. I'm going to make a dot fit function for this class. I'm going to define fit. What's fit looking for? Fit is looking for everything that feedforward and backpropagation is looking for. So an x value and a y value. In addition, we need to know how many epochs that we're going to train for. I'm going to set the default to 1. And I'm going to allow myself to change the learning rate if I want to when I call the fit function. So I'm going to be looking for learning rate. I'm going to default that to 0.01. Okay, so the first thing I need to do is I need to update the learning rate if I pass a new one. And that's going to be equal to LR. And now's where we get into that for loop that we made for the gradient descent video. So for I in epochs, in range epochs. All right, so for each of the epochs, we need to call the feedforward function followed by the backpropagation function. And just in case, I'm going to call an np.random.seed just in case I missed something that was supposed to be random. And we can go ahead and do a self.feedforward. And feedforward is, again, looking for x, followed by a self.backpropagation. And that's looking for x and y. And now, once we go through, again, we need to know the loss just to keep track of it. So loss is going to be equal to, we need to make a function. So going back up to the top here, I'm going to define a new function called calcLoss. And what it's going to be looking for is the predicted values of y hat and the true values of y. And for this loss, I'm not going to use log loss. I'm actually going to go ahead and use mean squared error, which is going to be equal to y minus y hat. So the true values minus the predicted values squared. And I want to take the mean of it. So this loss will be mean squared error. And if I go back down here, I can call that function. Now, y hat, again, is going to be self.output. And the y values are the y values I passed in. Okay, so now we have the loss. Like before, I kind of want to just graph it as we go. So I'm going to make a dictionary to store all my losses in. And I'm going to go ahead and assign that right now. So I want to say the key is equal to I, and then the loss is what the value is going to be. Okay. So we've gone through and we have run the feedforward and back propagation. Last thing, again, is I want some sort of status message to see how far along I've gone. So if the I plus 1, since we're starting at 0, mod, let's do 100. If that equals 0, so every 100th epoch, you need to print me a message. And we will use, let's go ahead and print the epoch. And that is going to be equal to I plus 1. And let's print the loss. And the loss is going to be fairly big value with a lot of decimals. So let's round that to, I don't know, 3 or 4 decimal places. So let's round it to 3. And that'll be good for now. We can add more later. And the last thing I want to do is I want to, like before, print that loss function as a graph. So we can create one more function called plot loss. Okay, so plot loss is going to be looking for that loss dictionary. So I'm just going to call it loss. And we are going to be using pyplot. So plt.plot. And it's going to be, again, this is a dictionary, so the x values are going to be the keys, and the y values are going to be the values. Okay, and if I go up here, I'll grab the title and the y-axis and everything. Alright, so the title for this is going to be training loss. The X label is going to be the epochs, and the Y label is going to be the loss. And I'll do one more thing, just turn on the grid to make it look a little better. Okay, so we now have plot loss, and I can come down here to the bottom, and outside of the for loop, I can go ahead and call it. So that'd be self.plot loss, and I'm going to pass it the loss dictionary. Okay, I am going to stop here and try to train the model to make sure I don't have any errors, which I do already. This was not supposed to be for, this was supposed to be an if. Okay, let me define the model, and then I'm going to go ahead and try to fit the model. So it would be neural network.fit, and if you remember up when we calculated the data, we have xtrain, xtest, ytrain, and ytest. So we are going to be passing in xtrain and ytrain. Now fit is also looking for epochs, so let's go ahead and say epochs is equal to 1000. And we're going to set our learning rate to be equal to let's go with 0.001. So 3 zeros and a 1. And let's go ahead and run it. All right, I do have an error. I spelled backpropagation wrong. Propagation. All right, d sigmoid. Yep. So I did not include self here. And there we go. So you can see every 100 epochs is printing out a message. The loss is going down. If we plot the loss versus epochs, we see that curve like we should be seeing. So everything's working really well here. Now, if you remember, the last thing we did on the last video was to create a predict function, and I want to do the same thing here. So within that class, I'm going to make one more function called predict. And predict is going to be looking for some x values. Now, if you remember when we predicted before, all we have to do is do the feedforward function without the backpropagation, and that is a prediction. So I can do self.feedforward, and I can pass it whatever x values I'm trying to do. And then all I need to do is return the self.output. Again, it's the output layer is where those y hat values live. And that's all I need to do for predictions. Now, I'm not going to call it outside of here. I'd rather want, every time this epoch's printed, I want to know what is my training accuracy and what is my testing accuracy. So I'm going to modify this fit function a little bit. And instead of just x and y, I'm going to pass it xtrain, ytrain, xtest, and ytest. Okay, so I'm passing it training data and testing data because when I go down here, I am going to want to, every 100 epochs or whatever I set this limit, I'm going to want to go ahead and figure out what my accuracy was. So I'm going to go ahead and make my training predictions. Now, when I calculate the training, let me see. I didn't add equals here. When I calculate the training accuracy, I'm just going to rerun the training data through the model and predict it. So that would be self.predict. I'm going to pass it xtrain. And before I forget, now that I changed all of these variables, let me go ahead and here every time where I had x when I was feed forwarding, I need to change these to trains now. And the same thing for the y values. That should be all of them. Yeah, you want to make sure you're now changing these to the training values. Okay, so back down to here. I want to predict on the training data just to see what my training accuracy was. And I'm going to do a dot round because I want to round those to zeros and ones. And I'm going to do the same thing for the test predictions. That's going to be equal to self.predict xtest. Round. Okay, so now we have our predictions. It's going to be a list of zeros and ones, and we also have the real values, which are the ytrain and ytest. So we can go ahead and do the accuracy using the function we imported from sklearn. So that would be, let's call it train accuracy is going to be equal to, and I want to round it, but it's going to be the accuracy score And now accuracy score is looking for your predictions and for your true values. So I will pass it train preds. So these are the predictions, and y train are the true values. And I'm going to go ahead and round this to 3 decimals. Okay. Do the same thing here, but I'm going to do test accuracy. And I'm going to pass it test predictions, and I'm going to give it the real y test values. And we will add these to this output message right here. So I want to know the train accuracy, which is equal to the variable I just created. And I want to know the test accuracy. Okay, so we're passing both of those into there. So now every 100 epochs, we should get a message with the epoch, the loss, what the current training accuracy is, and what the current test accuracy is. You know what, let me go ahead and give a little bit more precision here, since I'm not multiplying by 100. And let's go ahead and run it. Oh, I didn't. All right, so down here, we need to add those two data sets. So X train test and Y test. Okay. And as you can see, our training accuracy is going up and our testing accuracy is as well. If I increase these epochs to 5,000, all right, you're going to see the testing accuracy and for the most part the training accuracy stalls out after a while. It's not moving as fast as before, and it's very clear from this chart as well. So we would want to stop somewhere back probably 1,000 where I had it before. So I'm going to go back to that. And we can see we're back to that elbow in the chart. So that is how you implement your neural network in NumPy from scratch. I hope you found that fairly easy and fairly intuitive. Again, if you didn't see the first two videos, I highly recommend at least going back and watching the first one and the theory and the math behind it. This was a single hidden layer. It does get more complex as you add more hidden layers. You're going to have to keep using the chain rule, and your derivatives are going to get a little messy. But you can hopefully see how it would be possible to do it with more than one hidden layer, more than one activation function. There's a lot of different things you can do. Hopefully you guys got something out of this. Definitely hit that like button if you did. Subscribe to the channel for more stuff like this. I can't wait to see what I do next. I had a lot of fun doing this. I've actually never built a neural network from scratch, so this was a learning experience for me as well. Thanks guys, and I'll see you in the next video.